As you can see, the light bends, making the pencil look broken.
Oh, wow, look at that. It really is bent.
Guru Brahma, Guru Vishnu, Gurudevo Maheshwara, Guru Sakshat Parabrahma, Tasmai Shri Gurave Namaha.
Hello, physics enthusiasts. So, we've talked about how light bounces. But today, we're going to dive into something really fascinating. What happens when light passes through things? We're going to follow the bending journey of light, get to the bottom of refraction, see it in action with a glass slab, and figure out how we actually measure it all with something called the refractive index. All right, let's kick things off with a classic mystery. You've all seen this, right? You stick a perfectly straight pencil in a glass of water, and bam, it looks like it's broken right at the surface. So what's the deal? Well, it's a super cool optical illusion, and by the time we're done here, you'll know exactly how light plays this trick on our eyes. To crack this case, we're going to break it down into 3 simple parts. First, we'll look at the bending phenomenon itself. Then, we'll follow a single ray of light on a little journey through a glass slab to see the rules in action. And finally, we'll get into how physicists actually put a number on that bend. Let's dive in. You know, we kind of take for granted that light travels in these perfectly straight lines. And it does, as long as it's just cruising through one thing, like air. But the second it tries to cross a boundary, say from the air into a glass of water, all the rules change. And that's where it gets really interesting. And this brings us to our big word for the day, refraction. This is the official name for that change in direction that happens when light hits a new transparent material at an angle. That's it. That's the core idea. You change the medium, you change the direction of the light. Simple as that. And believe me, this is not just some obscure concept from a textbook. You see this stuff all the time. Refraction is the reason a coin at the bottom of a swimming pool looks shallower than it really is. It's totally the culprit behind our bent pencil illusion. And it's why a glass paperweight makes the text underneath it look bigger. Every single time, our brain is just getting fooled into thinking the light came from a different place than it actually did. Okay, so to really get a grip on the rules of this bending, scientists love to use a simple but brilliant tool, a rectangular glass slab. Because its surfaces are parallel, it lets us see exactly how light behaves as it goes in one side and out the other. So let's follow a single ray of light and see what happens. So here we go. There are 2 key moments on this journey. First, as the light ray enters the glass, it's moving from a rarer medium, which is air, into a denser one, the glass. And look what happens. It bends towards the normal. Now, the normal is just an imaginary line we draw straight up at 90 degrees to the surface. Okay, then, when the light leaves the glass and goes back into the rarer air, it does the exact opposite. It bends away from the normal. So, after all that bending, what's the final result? Well, because the 2 bends are equal and opposite, the ray of light that comes out is actually perfectly parallel to the ray that went in. Its overall direction hasn't changed at all, but its path has been shifted sideways just a little bit. And that nifty little shift has a name, lateral displacement. Okay, saying the light bends towards or away from the normal is a great start. But you know, physics, we need to be precise. So how can we actually measure this bend? How do we give a specific number to the bending power of glass or water or even a diamond? For that, we're going to need a law. And this brings us to a super important rule in optics called Snell's law. Now, I know it sounds a little mathy, but the idea behind it is actually pretty straightforward. It basically says that for any 2 specific materials, there's a fixed relationship between the angle the light comes in at and the angle it bends to. And that relationship always spits out the exact same number for those 2 materials. This constant number is the key to everything. And that constant number from Snell's law? Well, it has a name, the refractive index. And we usually write it as the letter N. This one number tells you everything you need to know about a material's power to bend light. But here's the really cool part. What it's actually measuring is how much that material slows light down. See, out in the vacuum of space, light is just a speed demon. It travels at its absolute maximum speed, a mind-boggling 300 million meters per second. But the instant it hits any substance, Air, water, glass, you name it, it's forced to slow down. And that slowing down is what causes the bending. The rule is simple. The more a material slows light down, the more it bends it, and the higher its refractive index will be. Now, we can measure this in a couple of ways. The relative index just compares the speed of light between any two materials you want, like comparing water to glass. But what you'll see most often is the absolute index. This is like the official score for a material. It compares its light speed directly to the ultimate cosmic speed limit, the speed of light in a vacuum. So let's make this real. The absolute refractive index of water is 1.33. But what does that number actually mean? It's simple. It means that light travels 1.33 times faster in a vacuum than it does in water. It's a direct measure of how much water puts the brakes on light. And this ability that a material has to refract light gets its own name, optical density. And the rule here couldn't be simpler. The higher the refractive index, the more optically dense the medium is. So since glass has a refractive index around 1.5, it's considered optically denser than water, which is down at 1.33. Okay, now this is a really important point, so listen up, because a lot of people get this wrong. As you can see right here, optical density is not the same thing as mass density. You know, how heavy something feels for its size. Take a look at kerosene. It's less dense than water, right? That's why it floats on top. But its refractive index is higher than water's. That means it's optically denser. Even though it's physically lighter, it actually bends light more than water does. Pretty wild, huh? All right, let's do a quick recap of the big ideas. Number 1, refraction is just the bending of light that happens when it changes speed by going into a new material. 2, light bends towards the normal when it enters an optically denser medium. 3, it bends away from the normal when it leaves. And 4, we measure all of this with a refractive index, which is really just a score for how much a material slows down and bends light. So we're left with this really powerful thought. We don't just know that light bends anymore. We know the rules, we know why, and we can measure it with incredible precision. And this all leads to a huge question. How can we use this? How can we harness this predictable bending to control the path of light, to focus it, and to build the incredible tools, from eyeglasses to massive telescopes, that have literally reshaped how we see the universe? Well, that's a story for another time.